Hi guys, welcome to Learn Electronics Repair. I have some PCBs here from PCBWay.com. These are very small, you can see, not very big at all. What are they? Oh, just over 3 centimeters. Just over 3 centimeters. 3 by 3.5, something like that. So yeah, they're a very small PCB. And this is a simple inverter project. So this is designed to run from the 12 volt supply and generate a 240 to 20 volt, something like that, output. And you can see that this doesn't contain any integrated circuits. We have 2 MOSFETs, 2 transistors, a few resistors and a couple of capacitors, and that is it. So that's all that's involved here. Let's have a look at this project on PCBWay.com. And we can see the project here. This is the schematic, I think we can call that. This is actually a video that explains how this works. So this is by Easy One. He's a contributor from Germany. Now, when I say a contributor with PCBWay.com, you can actually upload your own projects and designs here. And if you wish, you can actually make them shared projects, which means that other people can download the project, they can build them, and you will get a 10% commission from any PCBs that are sold. So this is a great way to get your projects out there, get your name out there, and also make some money on the side as well. So here we have the project, how to make a simple inverter, 12 volt to 220 volt, using C1815 transistors. So we have 2 transistors. Okay, we can see the resistors, 12 volt battery. I'm going to use my power supply actually, 2 IFPFZHDO MOSFETs, which are very common MOSFETs. I don't know if I have the correct transistors, but I think, to be honest, just about any NPN transistor will do. But you can look up the datasheet for these anyway. And this contributor, Easy One, has a YouTube channel and uploaded a video. There's no audio on this video, by the way, apart from a little bit of music. There's no talking. We can take a quick look. So he's going to warn us first that this generates high voltage, which is kind of what we would hope it would do, being a inverter. Yeah, you'd expect it to actually do that. You see his channel here. Okay. He shows us the actual item built, so you can see it there. This is his original PCB, homemade, before we uploaded the project. So this was the prototype, and basically just shows us the project being built and the project working. So we can see it's working here. There is also the schematic again, so we can see this here. I can see actually this is what's called a multi-vibrator. So we have 2 NPN transistors with 2 capacitors. Doesn't tell us what voltage they are. Maybe we can work that out ourselves. I would say this has a supply, yes, supply coming in here of 12 volts, so probably 16 volt will be fine. Just the resistors. And this is an oscillator, so this will switch backwards and forwards between the 2 transistors. We used to flash lights with these things. I'm guessing this runs at around 50 hertz, but I don't know. We're going to find out. And we can see that the output from this actually drives the MOSFETs, and they drive a transformer. So literally that is all we have here, okay? Let's put this together and let's see how well such a simple circuit actually works. Firstly then, let's see if we have all the components. I know I have the MOSFETs. I have plenty of those. There we see some. Okay. IFPFZHDO, very common components. These are from AliExpress. Everything else is just resistors and capacitors, apart from the other 2 transistors, C1815. So that's actually a 2SC1815. Let me see if I have any. If I do, there will be poles. Let's have a look. So here is my little stash of transistors. As I say, these are all poles. But I do have, oh, in fact, I have some new ones. Interesting. Okay, so I do have the transistors. We can see there They are 60 volt, 150 milliamps, 400 milliwatts. So a fairly common transistor, nothing special. This looks very similar in ratings to this one. So this is BC337 NPN, again a very common transistor. The pinout is different, 50 volt, 45 volt and 800 milliamps. So this is a similar but lower rated transistor. If I can get one to fit in the board, it might be interesting actually. We'll build a project using these and then maybe try something like this or something else I can find, possibly with the correct pin out, okay? We can see base and collector are reversed basically, but I'm sure we can get those to fit. The other thing I need is a transformer, and we need a center tapped transformer. So the transformer should be 12012. This is out of an old powered mixer, so it's not actually the correct voltage. I'll show you what voltage this actually is in a minute. This is the primary. It has the highest resistance. I have it connected to the mains. It's not switched on at the moment, but it's connected via my current limiting light bulb. I've just clicked the power on here. If they shorted out, well, the light bulb would light up. If I touch them with both my fingers, it will hurt. Okay. If I touch one or the other, I'll be fine because I have an isolated main supply. So our transformer has a few different outputs, and the only one which is a center tapped output, or the only two, we have this one and we have this one. So let's measure the output from my transformer and let's see if it's close enough. Okay, if it's some other voltage like 15 or 18, it'll be interesting to see if the circuit will run. I'll use my bench power supply to select a suitable voltage to drive this. But imagine, I would think, this thing, if I put 25 volt capacitors in, I think it would run onto a 24024 transformer. I don't think there's anything else that would limit the voltage. We will see, okay? But let's check our transformer. I have my multimeter on volts AC. It's just reading some stray millivolts at the moment. I'm going to power this on, just make sure these things don't touch each other. In fact, what I'll just do, actually, I'll disconnect this one. I'm going to kind of stick it there. Okay, now it's trapped so it can't go anywhere. Much less likely to short something by mistake. We'll have a look at this winding first. I'm going to switch on. Okay, the transformer's on. AC. That has 32 volts. And that also has 32. So this would have run the amplifier plus or minus 32. This is probably plus or minus 50. Let me see. Oh, actually I have 6. That's interesting. I would expect to have more than that. Ah, bad connection. Yeah, 14.7. So this is a plus or minus 15. That means I'm going to build the circuit. I'm going to attach this transformer, and I'm going to set my bench power supply to run this at 15 volts rather than 12 volts, and I think that will work. I've switched the mains off now so we can disconnect this. So we're going to connect a light bulb to here, okay, and see if it lights up, and then we can check the waveform on the scope as well. Easy one isn't specific about the rating of this inverter. Maybe it says somewhere in the video, but as I say, there's no audio. Well, it just says we can get the PCBs from PCBWay.com, of course, right? But he says in the tags here how to make a 100-watt inverter. So I'm guessing this is 100 watts or thereabouts, okay? He mentions 9 volts to 220. I guess if you use a 909 transformer, that's what you would get. And this was an entrance into the second PCB design contest. So they have contests on here also on PCBWay.com. I think we're currently on the 7th design contest. So you can enter the design contest and you can win over $6,000, by the way, okay? That's another good reason to come to PCBWay.com. Now let's build the circuit and let's see how it works. I'm going to use a 72 watt light bulb. It's what I happen to have, halogen bulb, so we'll use that. That should be within the capabilities of this inverter according to what Easy One says. It may get a bit hot with the MOSFETs, we'll see. He doesn't show a heatsink on the video, so hopefully it doesn't need a heatsink. He isn't using a heatsink on here, by the way. I noticed he had his fingers on it though. Yeah, but I guess he's on the low voltage side. That was perhaps not the best thing to do. Watch. Okay. So we'll use my 72 watt bulb and let's see what happens. I'm suspecting this is some sort of energy saving lamp and it's maybe a bit lower wattage than that. Okay, so I'll get this put together. It won't take me very long and let's see how it performs. Okay, so I've built it. I've deliberately left the leads on the transistors very long, so we can probably play around with this a little bit. Certainly makes it easy to take some waveforms from it. This is the positive terminal. There's actually two. That is the negative terminal. And then this is the output going to the light bulb. This is your 220 volts AC. So what I'm going to do with this first, I'm going to power this up just with a black and red lead here onto my bench power supply, 12 volts, and we'll also try 15 volts. And I want to see that the MOSFETs are being driven. So that's here on the end of this resistor or the leg of the MOSFET, and the same there. Okay, we can use the oscilloscope and let's check we've got a good drive waveform going to the MOSFET, and if so, we'll connect the transformer and see what it does with that. I have my power supply there, pretty much 12 volts. Let's attach the power to our little project. It's drawing about 100 milliamps. That's a bit surprising. Is it doing anything? Let's just disconnect that a moment. I'll put the scope on. So we can see that is oscillating at 82 Hertz. Maybe a little bit of a strange value, but that's what it's actually doing. Okay, so 82 Hertz. We could change the value of those electrolytics if we wanted to slow it down a little bit, I guess. Put a higher value, or the resistors which are in that circuit, we could actually tweak that a little bit to get it closer to 50. I don't see why not. But let's connect the transformer with a light bulb and see if this actually works. Okay, I'm gonna just increase the supply voltage to 15. And you can see the waveform's a little bit higher now. Okay. Yeah, I'm just over 15 volts there. It's saying voltage peak to peak is 14.4. You can increase the supply a little bit. .6, 14.7. Actually, if I increase the supply more, the frequency changes. You can see it's going up, and the output actually isn't changing much. So the frequency at which it oscillates is dependent on the supply voltage. And that's about as much I can get out of it, okay? 14.7, 14.8. And that is with the supply at 15.9 volts, 0.13 amps, okay? 130 milliamps. Okay, I've connected the transformer, but I haven't put a load on yet. There's no light bulb fitted yet. So we'll switch on, we'll see what current this draws. Half an amp almost, yeah. The oscilloscope, we can see we have 11.9 volts. I'm going to turn the power supply up a little bit towards 15. And you can see the frequency increases with the voltage. Can you see that? But if I keep going up, the voltage won't really increase anymore. It's running to 100 Hertz now. It's at 14.2 volt. Okay. Let's see if we have any voltage coming out of our PCB, our inverter. Let's see if our inverter is generating any output. So we'll go to volts AC onto this little terminal block I've fitted. What do we have? 245 volts. Well, that looks promising. Just switch it off. We'll put a light bulb in and we'll see what it does. So this bulb is rated at 72 watts. Now let's think about this. If that's 220 at 72 watts, yeah, without worrying about the difference between AC and DC, just to get an idea, we actually have 240 volts coming out of this, 72 watts. So watts is voltage times current, so watts divided by voltage is current. So 72 divided by 240 is about 300 milliamps. That makes sense because 220 watts 3 times would be 1 amp. Yeah, okay. So assuming it's 100% efficient, which it won't be, then we have 72 watts divided by 15 volts, 4.8 amps. Okay, and my bench power supply can only go up to 5. I do have one which goes up to 10. So this is going to draw some power. Yeah. It might just go bang. I don't know. Let's see. I should have more faith in it. Yeah. So we see our light bulb there. We have our PCB there. We have our transformer there. I'm going to switch this on. You can see the bench power supply. What's it do? It lights up. And it draws about 3.2 amps. So it's not generating the full voltage. Yeah. It didn't blow up. That's a good sign. What voltage do we have here now? Yeah, try again. 120. So about half. Yeah. We can have a look at the waveform. We have it there. It's about 10 volts peak to peak, or 12, yeah. So much lower, even though the power supply is still on, well, about 17 volts actually. Okay, right. It's still running at 85, 86 hertz. It could be, maybe the transformer is not quite so efficient at that frequency. I don't really know with mains transformers. We could look at the circuit and we can see the timing component. So we have the 1k resistor and the 10 microfarads. We have 1k, we have 10 microfarads. I think what I'm inclined to do as an experiment is to put something like half the value and wire in a little trimmer pot, so we can increase that and we can just play around with this so we can get a evenly spaced frequency at 50 hertz. Okay, so put some 500 ohms in and we will put yeah, trimmer pots as well. We don't want to just put a 1k trimmer because we don't want to be able to set this to 0. Okay, so we'll start off with a resistance because we're going to blow something up, the transistor in fact, because without that resistor there, the current will just flow straight through here. Yeah, so we need to leave a resistor plus a trimmer pot. We'll play around again with the transformer not attached because it didn't seem to make much difference to the operating frequency at all. And let's see if we can get this run at 15 volts at 50 hertz. I've actually left the 1k resistors in. I've put 2 1k pots in. I've set them to the center position, and you can see on the oscilloscope we're now running at 60 hertz. That's pretty much close enough, I would think, but let's just see what happens if I adjust this. I've disconnected the transformer at the moment, by the way. That's increasing the frequency. Let me adjust the other one as well. I'm trying to keep them kind of balanced. That increases. That also decreases. Okay, we have 50.2, 50.3. It's a little bit fiddly to try and set it exact, but that really is close enough. Ah, 50. Okay, I've got. Okay, so we have 50 hertz now on the scope. I've now attached the other scope probe so we can see both of these together. We can see they're running in antiphase to each other. The power supply is set to 14.7. I'm getting around 14, 15 on here, 14.9. I don't know exactly how accurate the voltage meter is on my power supply anyway, or for that matter, the scope. In fact, they now both say 14.7. Okay, so that looks good. 50 hertz, plus or minus 0.1 of a hertz. Let's see what voltage we get out of the transformer. Now, I just noticed, because I was going to solder the wires back on, that something's getting quite warm on here actually. Let's see what it actually is that's warming up. Okay, power on. It's the transistors, I think, the small ones, not the big ones. Big ones are further back, they're cold. No, it's the resistors. Look, you see the resistor here is at 52 centigrade, and here is at 70 centigrade. Okay, so in fact it's this one and this one, I think, that we're getting warm. One was very close to the edge, so I'm going to say it's this one. We'll double check. Yes, I've just put a point to it as that one. Okay, I wonder why they're getting hot. Let's see which ones they are. These are the 220 ohm resistors. Yes, those are the base drive, which is interesting actually. We also have the gate connected here as well to the same point, but this is the one that's getting hot on both sides. That's quite interesting actually. I'm a little bit surprised by that, but the transistors themselves are quite cold. Okay, I've added another camera so we can see the power supply as well. We can see the scope, we can see the multimeter, everything's clipped together. Let's see what this actually does now. Well, it actually gives less voltage than it did before. Yeah, that sort of makes sense, because you would think a transformer would be more efficient at a higher frequency. That's what I would have thought, but you know, I thought maybe mains transformers kind of operate best at 50 hertz. I think we've proved that isn't generally the case. I suspect there is a best frequency they run at. Are those resistors getting any hotter now? Let's see. And in fact, they're running cooler. Okay, they're running cooler. Although the voltage we're getting out of this is much lower, I can see it's 11 volts peak to peak. The output transistors, they don't get hot. In fact, they're cold. Okay. Yeah, so that's like quite interesting. I think we have enough now to chat, guys, about this. Okay. Obviously, the inverter does work. It's a very simple circuit. It works. It's interesting that I get, well, you've seen the voltages I was getting out of this, around 50% of what I expected with a load on than I was getting with no load. So basically with no load at the original frequency, I was getting 240 volts. That decreases with a load. So get into the comments below and let me know what you think. Yeah, I'm sure we can play with this a little bit more. Quite probably on the next live stream, which is around 10 days from now. That might be a good time to play around with this. So get some suggestions in. Let me know what you think. And then on the live stream, let's try if we come up with anything interesting. How can we get more voltage out of this? And why are we getting a low voltage under load? Yeah. So I'd like to thank you for watching. I'd like to thank PCBWay very much for sponsoring these videos, for making this all possible. And I look forward to seeing you all again soon on Learn Electronics Repair. Ciao for now, guys.